we're at lecture 14 on the Poisson process, which is illustrated right below me. So we're going to dig into that picture with some definitions. The first definition is looking ahead quite a little bit to continuous time Markov chains, but nevertheless, we all know what a Markov chain is, and we know what a state space is. So if we think of the Poisson process as a Markov chain, the state space will just be the natural numbers. So you see on the y-axis on that picture, the values on the y-axis are 0, 1, 2, 3, 4, 5, and so on. Those are the values that the Poisson process will assume. And the additional terminology for Markov chains is the one-step transitions, or just transitions in general, what transitions are possible in one step. Those are all going to be of the form x to x plus 1. So in other words, whatever state we're in, let's say it's state 3, the next one always has to be the number 4. If we're at state 11, the next state will be 12, and so on and so forth. The one difference from discrete time Markov chains is that the time is going to be a little bit more dynamic. In other words, in discrete time Markov chains, time was this kind of static 1 unit increment, 1, 2, 3, 4, 5, and so on. Whereas in continuous time Markov chains, we're going to give those intervals a certain duration. And in particular for the Poisson process, the amount of time that we remain in each state is going to be exponentially distributed with a rate parameter, so with the parameter 1 for the standard Poisson process, and an arbitrary parameter, as we'll see later, for a more general Poisson process. So these times that we remain in each state, those on the picture below me, you can kind of see it as the steps, in the length of each one of those steps on that staircase. So the time t3 minus t2, the length of that step, is an exponential random variable, or was generated according to that distribution, with it being parameter 1 for the standard Poisson process. So here's the general definition of an exponential distribution, which I'm sure you're familiar with. So if we're looking at a random variable tau, and that random variable has the exponential distribution with some rate, let's say mu, not necessarily 1, but just some arbitrary rate mu, this would be the cumulative distribution function for this random variable. And you notice that it's non-negative, so it's modeling a time, which we kind of intuitively think of as something non-negative. Here is a list of a bunch of statistics, so you can see the expected value of an exponential random variable is 1 over its rate, which is fairly reasonable. If we think of the word rate, it means how frequently something is happening, or how soon is something going to happen. So if you have a large rate, large mu, the expected time until, the expected length of time that we wait is small. Whereas if the rate is small, then the expected time that we wait is long. A small rate means something happens infrequently, so we wait a long time. Then there's also the variance and the moment generating function that are both included in the calculations there, but we'll return to these later on. They're not terribly important as of right now. So I just kind of want to summarize this picture again in terms of what we saw. We know by now that the Poisson process is always going to have this staircase type of behavior to it, where it will essentially count events. So it will move between natural numbers starting from 0, then the next move will be to 1, the next one to 2, to 3, to 4, and so on. And the lengths of time that we wait in between each count, here I'm calling them tau k, will be exponentially distributed with rate 1, at least for the standard Poisson process. So that's the picture we have in mind. Here's the definition that I want to dig into, mostly because it should remind you of another process that we studied, namely the Brownian motion. So let's go through this definition step by step. So this is defining the standard Poisson process, and it's gonna require it to have what are called counting paths. Remember, the Brownian motion had continuous paths. This one is gonna have something called counting paths, which is kind of is reminiscent of the picture again that we see. It starts at 0, same as the Brownian motion, and then satisfies the following two properties, which are properties of the increments of the process. Again, just like the case of the Brownian motion. So the increments are stationary and independent. We'll look again at what these definitions are, but this is identical to the definition of the Brownian motion. And then each increment, so how much the process changes between 2 times s and t, here s is less than t, so that nt minus ns is an increment, that as a random variable will be Poisson distributed with parameter t minus s. So that's the definition, and we could look at kind of each ingredient step by step. First of all, the counting path, I think you intuitively see what I mean. Let's just define it a little bit more rigorously. So the first part of the definition of a counting path will be a step function. I think you're all familiar with step functions. These are functions that have constant values on intervals. So you pick a bunch of times. So S0 through Sn, S0 is 0, so I guess we're just picking S1 through Sn. And that will define kind of like a little discretization of time with these half intervals combining to form the entire real number line. And on each one of these intervals, a step function is going to remain constant, which is exactly, again, what you see in the picture. The one addition for a counting path is that the step function must be increasing, which is, again, what you see on the picture. So the count always goes up, never goes down. Step functions in general can go down, move down a step. Here we're always moving up, and moreover, we're moving up always in jumps of size 1. So every time we count, we move up by 1, hence the word counting. So that's what it means to have a counting path. Just in summary, it is an increasing step function with discontinuities of size 1, or with jumps of size 1. Here are the two remaining properties. So let's look at the first, I guess this part of it, the last part, independent increments. If you look at a bunch of increments here, there are m of them, and you look at their joint distribution, if that distribution is just a product of the marginals, you know that those random variables, just quite generally, those random variables will be independent. So this is what it means to have independent increments. The next part could be stationarity. So in other words, if you pick an increment of the same length, say you pick an increment that has a time length h, so the duration of time allowed is some fixed length h, regardless of where you start the increment. Here the increment is started at t, and here the increment is started at s, so those are presumably two different numbers. The probabilities involved don't change based on the starting point. They change only as a function of the duration of the increment. So h here is the duration of the increment, and you can see that the probabilities assigned to these increments don't depend on the starting time. So this quantity here doesn't depend on s, it doesn't depend on t, it only depends on the length of the increment. That's what it means for the increments to be stationary. And finally, this specific form is actually something that's Poisson distributed with the parameter as the length of the increment. So we're going to look at the next slide, the definition of the Poisson distribution, but this is what it is. So here is the Poisson distribution. So while seeing Poisson random variables, so if you have a Poisson random variable k, and it has a parameter, sometimes called the rate mu, this would be the associated probability distribution function. So the values allowed are natural numbers, 0, 1, 2, 3, and so on. And these are the probabilities that it assigns to each number. So you can see that when n becomes large, this probability should become very small, and so on and so forth. I'll have a picture on the next slide. But as it relates to the increments of the Poisson process, those have the Poisson distribution. So coming back again to here, item 1 says the increment nt minus ns better be Poisson distributed with parameter t minus s. That's exactly what you see here. So in this expression, I replace the mu, the parameter, with the length of the time associated with that particular increment. And then more generally, as we'll see later, if we're thinking of a Poisson process of rate mu, then these would be the distributions for each increment. So you just have a little multiplier mu here next to the time duration for the increment. This is what the Poisson distribution looks like. This is straight out of Wikipedia. I don't like the fact that they're using lines to interpolate this. So the Poisson distribution is concentrated on the natural numbers. So the value, say 5.5, has 0 probability. But you can kind of see here with the rate being denoted by lambda, not mu, you can kind of see the structure of the distribution. So when lambda is here 10, you can see how the distribution concentrates around that rate parameter. Same thing for lambda equals 4. You can see kind of the peak of the distribution is around the parameter of that distribution. And going back to the increments, the parameter is equal to the length of time that passes in between each of the increments, the starting and the endpoint. Okay, so we're back at the definition here. This is just a review again. Independent increments, stationary increments, and increments of that are Poisson distributed with the parameter determined by the length of the increment. And what I want to bring up here is that this looks remarkably like what we saw for the Brownian motion. The only exception, well, there are a couple of exceptions. One is instead of counting paths, you have continuous paths. And the only other difference that I see is that instead of Poisson distributed increments, you have normally distributed increments. But the rest is just remarkably similar. And so what we'll do in the next clip is try to kind of see why this should be. And for that, we'll have to revisit the random walk.